All right, it's just about 8:30, so let's get started. Hello and welcome back to Math 127. I hope you all are having a good week, trying to stay healthy, make sure you're staying hydrated. People are dropping like flies left and right, catching all sorts of things. So try to be proactive and make sure you're staying as healthy as you can, get lots of rest and the things you need to stay well. So today we are just continuing through chapter 2. So we've already done limits and continuity, and then last class we talked about the instantaneous rate of change, which we learned was the derivative. So what we're going to be doing today is we're going to be generalizing what we did last time for looking at the derivative at a point and moving it to understanding about the derivative as a function. Okay. So I'm going to go ahead and turn on the dot cam here. Give me 1 second. Screen share. Okay. Turn on the light. Okay. And so today, like I said, we are going to be talking about the derivative function. So again, I just want to remind you that last time we were really considering the rate of change at one value at a particular point. And we tried to get close to that point by getting really, really close to the value we were interested, a little to the left and a little to the right, and doing average rates of change in order to figure out what the derivative or the rate of change was at that point. So now that we understand how to find the instantaneous rate of change at a point, we want to be able to generalize that to a function. So what does that mean? That means we want to be able to take a function and figure out the derivative function, which will allow us to find the rate of change at any point. So this is why we sort of did a small foray into limits and continuity, because the actual definition of derivative is defined using limits. So the definition of derivative says that for any function f, we define the derivative function, which we said we could notate as f prime of x, by this particular limit. So it's the limit as h goes to 0 of f of x plus h minus f of x over h. And we'll talk about this limit in a second. But of course, it only works if the limit exists, right? So we said the limit will exist if it's the same from the left and the right. And the functions that we will look at, they will all exist for when we're talking about the derivative function. And so we use the term differentiable if the derivative exists. So why this limit? What is this limit doing? So I'm going to draw a picture so we can visualize what this particular limit means here. So let me straighten that out a little bit. So if we have some function, right, and it can look like anything, and we're interested in what's happening between 2 points, we can call those points x and x plus h, right? So this is just some value, and this is some value plus a little bit. So we can notate the functional value over here is f of x, and this one as f of x plus h, right? If we were to plug it into our general function here. And so our approach was to find the average rate of change between the 2 points to start, right? That's how we were looking at it last time. And so here, if we were going to set up the average rate of change, that would be f of x plus h minus f of x. So that's the change in y, divided by the change in x. So that's x plus h minus x. So notice here that the x's on the bottom will cancel. And we end up with f of x plus h minus f of x over h. So that looks very similar to what we have here. So why the limit? So remember last time we wanted to get closer and closer to the point that we were interested in. So we want this point to get closer and closer to the point we're interested in. So how do we do that? We let h go to 0. So if we take the limit as h goes to 0, we are essentially bringing this point closer and closer in all our calculations. So that's where this formula comes from. Now, the reality is we're not going to be using this formula a whole lot for what we're doing, but we can certainly use it to sort of understand what's happening in the background. Okay, so how do we use this limit and how do we think about why it works, right? So what we're going to do is we're just going to do two examples. We'll do one together and then I'll have you try one where we try to figure out how we apply what we know about limits and this formula, which also has composite functions, and use it to find derivative functions. Okay, so like I said, we're going to do one together and then I'll have you try one. So here we want to start by finding the derivative f prime of x of the function x squared. So if we were to apply this function here, this formula, this limit formula, we have f of x, right? That's given, that's the x squared, but we also need f of x plus h. So on the side, I am just going to figure out what that is so that I can then set up my limit. So f of x plus h, now we need to think back to when we talked about composite functions, right? And so that means we're going to be plugging in an x plus h into our x squared function. So here we have x plus h squared, right? Because again, we're taking x plus h and plugging it into the f of x given function. So we will need to multiply this out at some point. I'm not going to do it in this step. We'll do it in the next step, but you could multiply it out here. So we want to set up our limit to find the derivative using these pieces. So f of x plus h, we said is x plus h squared minus f of x. Okay, so that means we're subtracting off an x squared, all divided by h. So I applied these things to this particular function, and now I have something that looks like this. So if you remember back to when we were talking about limits, we talked about how sometimes it's helpful to simplify a function before you do the limit. That's what we're going to do here. So the limit as h goes to 0. Now if I to square this out, I'm going to have x squared. I'm going to put this in parentheses so I can see which part is the squared out part. Plus 2xh will be the cross term because there'll be an x times h and then another h times x. And then plus h squared. So that's what I get when I square out this term. And then I have a minus x squared all divided by h. So what I'm trying to do is I'm trying to see if I can simplify anything. Okay, so here, notice I have an x squared and a minus x squared. So those are going to cancel, right? So that means I have the limit as h goes to 0 of 2xh plus h squared over h. So as you can imagine, at this point, I still can't really see what happens as h goes to 0, because that would give me a 0 in the denominator. And I really don't want to do that, right? We don't want to divide by 0. So what I'm going to do is I'm going to factor out an h term in the numerator. So there's an h in each of the terms. So if I pull that out front, I'm left with 2x plus h over h. The reason I wanted to pull out that h is so I can cancel the h that's in the denominator. That's going to be helpful for me because now I'm not worried about having a 0 in the denominator. So I'm left with the limit as h goes to 0 of 2x plus h. So one of the things I can do here, this is a polynomial term. Okay, so that's x squared, x cubes. If your function is in polynomial form, you can just let the limit do what it's going to do as long as you're not dividing by 0. So in this case, I can actually let h just go to 0. I could do it from the left and the right, but as you can imagine, if h goes to 0 from the left and the right, both times you're going to end up with 2x. So what does that tell me? That tells me that if I start with the function x squared, and I want to talk about the derivative for any point on this function is going to be 2x. So that means that if I am considering x squared, right, which is a parabola, and I want to know the slope of the tangent line at 1, right? Because remember, the derivative is the slope of the tangent line. I can find that slope by plugging the value of 1 into my derivative function. So f prime of 1 is 2 times 1, which equals 2. So now I know the slope of this tangent line is going to be 2, and I know that my function is changing at a rate of 2 units in the dependent direction for every one in the independent direction at this particular point. I could also find the slope of the tangent line at -1 by plugging in, or at 0 by plugging in. So by getting the function, I'm able to find the derivative for any point. So that's the value of doing this with limits. I do want you to try one to really sort of understand what's happening in the background. So I'm going to have you try this next one, where our function is f of x equals 2x squared minus 3x. And I want you to set up the limit like I did here. I want you to simplify algebraically however you can, and then take the limit as h goes to 0. And once you have your limit, then you have your f prime of x for this function. And once you have that, I want you to plug in 0, like I did with the 1 here, to get the slope at 0. So I'm going to give you 2 or 3 minutes to set this up. See if you can work out, again, some of the algebra. Be careful here, but feel free to check in with someone next to you. And if there's TAs there, they can walk around and help you if you have any questions, and then we'll go through it together in about 2 or 3 minutes. All right, take about 30 more seconds to finish up whatever part you're working on. All right, I am going to do a quick stop share and then reshare because it seems a little blurry and I'm not sure why. Let's see. Let's see if I reshare it, if it is a little less blurry, hopefully. Oh, well, that switched. Why did you do that? Let's see. All right, hold the phone, everybody. Okay, hold on, let's see. That is backwards. Why are you backwards? Okay, hold on. See if that works. Ah, there we go. Much better. So we're going to walk through some of the algebra here, and hopefully this is okay for you and you feel comfortable with this algebra. But if for some reason you're getting lost in the algebraic steps, please make sure you stop by Drop In Help so we can sort of work out this a little bit more for you. So again, we want f of x plus h minus f of x. F of x plus h means we're going to go to our function, and wherever we see an x, we're going to substitute in an x plus h. So the f of x plus h term will be 2 times x plus h squared minus 3 times x plus h. And I put this in brackets to help me sort of separate the different things that I'm doing. And then minus, we need to subtract off the f of x term. So I also just put that in brackets to keep them separate. So in the first couple steps, I'm just working within the first bracket to simplify. So first I squared out the x plus h. So x squared plus 2xh plus h squared. And then notice I still have the 2 and the 3 that need to be distributed. So I'm going to distribute the 2 through the first term and then the 3 through the second term from just the f of x plus h term. So when I distribute the 2, I get 2x squared plus 4xh plus 2h squared. And then here, when I distribute this minus 3 through, I get minus 3x and minus 3h. Notice that the minus also goes to both terms. So far, all I've done was sort of simplify this first bracket, and the second one just comes along for the ride. So now that I have everything squared out, I want to combine any like terms and cancel anything that may cancel. So I want you to notice here I have a 2x squared, and I'm going to have a minus 2x squared here. So those will cancel because we have a positive one and we have a negative one. We also have this minus 3x, and then over here, this is also a minus 3x, but this minus is also going to get distributed. So this is actually going to become a positive 3x, and this is a negative 3x, so those will cancel. Okay, that one's a little bit trickier to see. So now that those are canceled, we have the limit as h goes to 0 of 4x plus h plus 2h squared minus 3h. Now both of these terms are gone, all divided by h. So like last time, I'm still a little worried here. I can't let h go to 0 yet because of my denominator. So I want to factor out an h right here from the top. That's 4xh, not 4x plus h. So when I factor out an h, I get 4x plus 2h minus 3, all divided by h. So the h's cancel here. And now, if I let h go to 0, the function that I'm left with is my derivative. So here, the function that I'm left with is 4x minus 3. So that's a derivative function that will tell me the slope of the derivative at any point. Well, remember, I'm interested in what's happening at 0. So f prime of 0, the slope of the tangent line that touches this function at 0, will be 4 times 0 minus 3, which is negative 3. Okay. Now, these are pretty long and pretty algebraic. We don't do a ton of these in this class. What we do is we're going to end up with some formulas that we'll use in chapter 3, but it is important to understand why we had to think about limits in order to then be able to talk about both the instantaneous rate of change last time and the derivative function this time. So it is important to be able to apply this definition. There might be one homework problem on it, and there may be one on the quiz that would be probably more like the first one in terms of the algebra. But most of the work we're going to do on the derivative function is going to have to do with evaluating it graphically. Because like I said, later we're going to get some more sort of straightforward formulas to deal with a lot of these functions. So we're going to sort of switch gears, and we're going to start looking at a graph here. And so, as I mentioned last class, one of the first things we want to be able to do is really think about, is the function positive, negative, or 0 when we think about the derivative at a point, right? So if we're talking about the derivative to the function that we have here, which we'll call f of x, at each of these points, right, we should be able to think about the slope of the tangent line to think about if it's going to be positive, negative, or 0. So first we'll do that, and then we'll take it a step further and see if we can actually approximate the slope of the tangent line by drawing it in. So what I want you to do is I want you to take a quick minute, and above each of these numbers, I want you to write either plus, minus, or 0 for whether you think that the derivative or the instantaneous rate of change will be positive, negative, or 0, again, based on trying to visualize the tangent line. Okay, so take a minute to just think that through and jot it down. Okay, lock in your guesses here. So let's quickly go through positive, negative, 0, and then we'll take it a step further and actually approximate the derivative numerically. So at negative 2, that's the point that's right here. If I try to think about the tangent line, it's going to be downward sloping, and so the derivative will be negative. At negative 1, again, if I think about that tangent line, it's going to be downward sloping. So that one will be negative as well. When I look at what's happening at 0, this is where I'm going to have that horizontal tangent line, right? It's going to sit right here going straight across. So that one's going to be 0. At 1, if I think about the tangent line, it goes in the upward direction from left to right. So that's going to have a slope that is positive. And then at 2, again, it's going to go up from left to right. So that one will also have a slope that is positive. So that's what we were doing last time. Now we want to make it a little more formal. And for each of these points, what we want to do is we want to approximate the slope of the tangent line. So how do we do that? Well, we have to sketch in the tangent line and try to figure out 2 points on that line to calculate the slope. Because remember, we're looking for the slope of the tangent line. So we're going to do the first one together. We'll do negative 2 together, and then I'll have you try the other ones. Okay, so for -2, okay, I've drawn in the tangent line here. I didn't sort of trace the cross lines as much, but I wanted to just give you the sketch of how we do this. So when we do this, right, you're going to draw a point at -2. So I went down to -2, I went up, I drew in the point, and that's the point -2, 4. From there, I sketched in a tangent line. I know it has to be a negative slope, and I tried to find another point on this line that would be helpful for me to calculate the slope. So to me, it looked like it went through at -1, 0. So to approximate the slope here, what I'm going to do is the change in y over the change in x. So I'll do that up here for a moment. Okay, so the change in y, I'm going to do 4 minus 0 over the change in x. So if I started with 4, I need to start with -2 down here. So -2 minus -1. Be careful with your negatives and minuses. So I end up with 4 divided by -1, which is going to give me a slope of -4. So if the slope of my tangent line here is -4, what that tells me is that the derivative at -2 is approximately -4. So over here, if we go back here, we said that we knew that the slope was going to be negative, and now we have an approximation for it. Now we know that it's going to be approximately -4. So how do we write that? We write f prime, and this was at -2, we think is going to be -4. Okay, and again, the process on how I do that, I go to -2, I go up to the function and draw the point. So I get the point where I touch with the tangent line. Then I sketch in a tangent line, and I have to approximate a second point on the line. And then I do change in y over change in x. So I want you to try this for the other points that are here. So at -1, 0, 1, and 2, I want you to try to come up with your best approximation for the slope of the tangent line at these other 4 points. Okay, so I'm going to give you about 3 minutes to try to work that out. If you have the picture in front of you, you can certainly sketch right on top of it. Otherwise, you might need to sketch a graph and sort of try to visualize those tangent lines here. So if you can't see it, this is 0, 1, 2, 3 across the bottom. And then as we go up, it's 2, 4, 6, 8 is the scale. Okay, so take about 3 minutes, see if you can figure out those other slopes, and then we'll come back and do it together. All right, take about 30 more seconds to finish up whichever one you're trying. All right, so let's take a look at these. I do want to mention there's a little bit of an art to drawing in tangent lines. If you are trying to approximate a tangent line on a screen, I'll often recommend using like an index card as a line to sort of visualize what points it crosses through. And if you have it on paper using a ruler, I think it's a little bit easier to get the exact tangent line than freehanding it. But, as long as you're in the relative range of what we're getting, that should be fine. And of course, the sign should be the same, positive, negative, 0 as whatever I'm getting. So we did this one together. This was the one at -2. So the next one that we want to consider is what's happening at -1. Okay. So for -1, when I drew on my tangent line, the lines that I get here that are representing the slope. So I started by going to -1. And then for me, it looked like that point was halfway between 0 and 2. So I approximated the point where it touches to be -1, 1. So again, I recommend using the point where the tangent line touches because that's usually an easy one to figure out. Then once you sketch in your tangent line, you're looking for another point on the line, and it can be any point. I just try to pick points that seem convenient. So you may have picked a point up here that was convenient to you. That's fine. To me, this looked like it crossed through down here at 0, -1. So this is the -2 mark. So that's the second point that I used, but you may have used different points. So now when I approximate the slope, I'm going to do the change in y over the change in x. So here the change in y is going to be 1 minus -1. Okay, so that's the change in y. And since I started with 1, then on the bottom I have to do -1 minus 0. And so here on the top I end up with, so 1 minus -1. Those negatives are going to cancel. So I have 2 divided by -1, which gives me a slope of -2. So I know that the slope should be negative because it's going downward from left to right. So that also tells me here again that if I was approximating f prime of -1, that it gets approximately -2. So if you got a different approximation than me, you should still have something that's negative. So depending on how well you sketched your tangent line, you may have ended up with -3 or -1, which for now is probably fine, but it should be negative, right? So whatever points you picked and however you drew this at -1, you should be getting a negative value. And the more practice that you do at this, the better you'll get at drawing in these tangent lines. Okay, so the next one we'll look at is 0. So we're interested in what's happening at 0. So if you were to draw on the tangent line at 0, it's gonna lie on the line. It's gonna be right on this horizontal axis, right? The one that touches right at 0. So it definitely touches at the point 0, 0, and then it touches at all these integer marks. So at 2, 0, at 1, 0, at -1, 0. So any of those. So again, we know that if it's a horizontal line, that the slope is going to be 0. But if you also do change in y over change in x, you end up with 0 over 2, right? Which is still 0. So here we know that the slope at 0 should be 0 because we have this horizontal tangent line at 0. Okay. So let's look at the next one. Okay, so trying to look at the tangent line at 1, right? So here, again, I went to 1, I went up to where it touched. To me, that looked like it was at the point 1, 1, about halfway between 0 and 2. So I'm using the point 1, 1. And then when I drew in my line, it looked like it also crossed through at 0, -1. So again, one of the key things that's happening here is that we see that this is a positively sloped line. So our approximation should be positive. So again, when we do the change in y over the change in x here, the change in y, we're going to have 1 minus -1, right? So 1 minus -1 divided by 1 minus 0. That's going to give me a slope of +2. So I know that f prime at 1 is +2. And again, depending on how you drew your line for approximation, it might be slightly different than mine. You may have ended up with 1 or 3 or something in between, but it should definitely be positive, whatever that value is. Right? The difference in values will just sort of be how you drew your line. If you drew it a little more this way, you may have gotten different points than if you do it this way. Like I said, it's sort of an art drawing in tangent lines, but it should definitely be a positive value. Okay. And then the last value we're interested in is what's happening at 2, right? So here, I went to 2, I went up to my dot here. That's the point 2,4. When I drew in my tangent line, it looked like it crossed through at 1, 0. So those are the values that I used. So again, when we approximate the slope, we're going to change in y over change in x. So we have 4 minus 0 over 2 minus 1, which is going to give me a slope of 4. It's 4 divided by 1. So here, right, f prime of 2 is approximately 4. So again, it should be positive and it should be bigger than your approximation at 1, right? Because we should be steeper as we move to the right. So your approximations might not be exactly the same as mine, but they should be relatively close. So what we're going to do is we're going to take this sort of idea of these tangent lines and we're going to try to generalize them in a couple ways so that we can start thinking about how we draw the derivative. Excuse me, sneezed. So what we're going to do is we're going to go back. Maybe we won't go back. We'll just do it on this one. So what we're going to do is we're going to look at a graph. And we're going to see if we can figure out some intervals where our function has a pattern, right? So let me just darken this. So this is 1, this is 2, this is the 3 mark, this is the 4 mark, 5 mark, 6, 7. Okay. And so here we only really need the x values for what we're about to do. So what we want to do on this particular problem is we want to draw in a whole bunch of tangent lines, right? So this is -1 over here. So I want you to draw in maybe 7 or 8 tangent lines here, just wherever you see fit. And I want you to see if there's a relationship between the slope of the tangent line, so positive, negative, 0, and where this function is increasing and decreasing. Okay, so I want you to take 2 minutes, draw in a whole bunch of different tangent lines or visualize a whole bunch of tangent lines and see if they're positive, negative, or 0. So mark positive, negative, 0 on a whole bunch of them. And then see if you can figure out the relationship, again, between where this function, this f of x, is increasing and decreasing and the sign of the first derivative. So whether it's positive, negative, or 0, okay? So take, like I said, take 2 minutes, jot down a whole bunch of tangent lines and see if you can sort of work out that relationship, and then we'll go through it together. All right, take about 30 more seconds to finish up wherever you're at. All right. So what I did is I took my red marker, and wherever I drew in points that were upward sloping, I used red to find the positive places. I used blue to find tangent lines that I thought had a negative slope. And then I used green to find any place where I thought there was a zero slope. So I labeled all these tangent lines, and I'm trying to figure out if there's a relationship between the positive, negative, and zero values and where f of x is increasing or decreasing. So what I want to do is I want to section off my graph into chunks that are increasing or decreasing to see if there's a pattern. So here is where I sort of change from increasing to decreasing. And then here, so here I was increasing. Here I was decreasing. Here I was increasing again. Then over here I was decreasing again. Okay. So one of the things I immediately notice is that when I change from increasing to decreasing, that's where I have these zero sloped tangent lines, right? So the derivative is zero when I change from increasing to decreasing. I also notice that whenever my function is increasing, my tangent lines are positively sloped. And whenever my function is decreasing, my tangent lines are negatively sloped. So I can generalize this, because this will always be true, into the following statements. If f of x is increasing on an interval, so that means that the function is going up from left to right, then the derivative is positive on that interval. Okay, so wherever my function's increasing, my derivative is positive. Okay, if my function is decreasing, so here and here, then my derivative is negative, because again, that means that the slope of this tangent line will have a negative value. And then if f of x is constant, so what does that mean? That's the point where we change from increasing to decreasing. We call that point constant. Then my derivative is zero. And it says on that interval, but this is really at that point. Okay. So these three statements are going to become three of the most important statements that we will use throughout the rest of this course. And I want to sort of point out some pitfalls that happen for students. So understanding the difference between increasing and decreasing and positive and negative on a graph are critical to doing our analysis. So we should be able to look at any part of a function and talk about whether it's increasing, decreasing, positive, or negative for the function, and then also be able to talk about the derivative. So here, in this particular picture, f of x is positive for all values. Okay, and what that means is that my function is above the x-axis. Okay, so whether or not my original function is positive or negative does not impact the derivative. Whether or not my function is increasing or decreasing does impact the derivative. And the relationship between the original and the derivative is that whether it's increasing or decreasing in the original function tells me if I am positive, negative, or zero for the derivative. So trying to keep all of these straight is going to be something we need to practice a lot. This comes up through pretty much every other section we will talk about after chapter 2. And if we can't get all these relationships straight, it becomes really confusing really fast. So we really want to hone in on these relationships because we're going to be adding a bunch more that we need to know in section 2.4. Okay, so let's take these three statements and see if we can do a problem where we are relating where the original function is increasing and decreasing to where the derivative is positive and negative. Okay, so again, I just want to remind you that at the point we turn around, we consider that constant, which means that at those values, we are not increasing or decreasing. So at 0, it's not increasing or decreasing, it's constant. At approximately 3 and at approximately 6, those are places where we are not increasing or decreasing, we are constant. Okay, so the next exercise we're going to try here is we're going to take a look at this graph and we are going to determine the intervals where the first derivative is positive, negative, and 0. So this is the original function, f of x, which it says in the setup. And we want to use f of x to figure out where the derivative is positive, negative, and 0. So we are going to be evaluating this function to see where it's increasing, decreasing, and constant. So I'm going to give you 2-3 minutes. I want you to work out where the derivative is going to be positive, negative, and 0 by working out where this function is increasing and decreasing. And then I want you to think about how you think we will write those intervals, right? So we've talked about interval notation before with open and closed brackets and things like that. So I want you to think about how we would do that to talk about and answer this particular question. Okay, so take about 3 minutes, see if you can work out those intervals, think about how to write it mathematically, and then we'll go through it together. All right, take about 30 more seconds to finish up whatever part you're working on. All right, so we know from the previous example that we really want to partition this off and look at where it's increasing and decreasing. So I'm going to try to separate where this happens. So it looks like at roughly 1.5, we change from decreasing to increasing. And then again at 0, we were increasing until 0, then we start decreasing, and then roughly positive 1.5 is where we sort of change again. So here we were decreasing, and then we were increasing, and then we were decreasing again, and then finally we were increasing. And so again, when I talk about increasing and decreasing, I'm talking about whether the function's going upward or downward from left to right. So I'm decreasing because these values are coming down, okay? So let's talk about these intervals. So here, right, I could make an argument for negative infinity if I think this sort of goes on forever, or I could cap it at negative 2.5. That's fine either way. I'm going to go with negative infinity, but if you use negative 2.5, that's fine. We're more concerned with what's happening sort of in the middle for right now. So negative infinity. Now this is going to go until 1.5. So I know that something's happening at 1.5, and the question is whether or not I need to use an open bracket or a closed bracket. And so the question is, am I including 1.5 in my decreasing interval? And the answer is no, because at 1.5 is where I am constant. Okay, so I'm not going to include it in that interval. I'm going to jump to the other decreasing interval, and then we'll do the increasing after. So here, decreasing, it starts at 0 and it, oh, you guys, that should have been negative 1.5. Sorry about that. For my other decreasing interval, I'm going between 0 and positive 1.5. And for the same reasons, I'm not going to include 0 and 1.5 as possible points where I'm decreasing, because I know at those points I'm constant. So I'm going to use the open interval notation to go 0 to positive 1.5. So that's where I'm decreasing. And we'll talk about how that relates to the derivative in a moment, but let's talk about increasing. So for all the same reasons, right, we are not going to include the point where we turn around. So I'm going to be increasing from negative 1.5 until approximately 0. And then again over here, from positive 1.5 off to positive infinity. Okay, so again, I'm going to use the open brackets. That's sort of the really important point here when I'm turning around, because at those particular points, I'm not increasing or decreasing. I am constant. So what does this tell me about the derivative? So remember, this is trying to help me figure out where the derivative is positive and where the derivative is negative. So again, my rules say that if my original function is decreasing, that my derivative is negative. So here on this interval, my derivative is going to be negative, right? For any value I pick on this interval, the derivative is negative. So from negative infinity to negative 1.5, I know my derivative is negative. Same thing over here, wherever I'm decreasing. So from 0 to positive 1.5, the derivative is negative. And I can convince myself this is true because if I pick any point on this interval and I draw in a tangent line, I can see that it has a negative slope. Okay. Now, when I have my function increasing, so going up, that's when I know that my derivative is going to be positive. So any value that I pick in here, if I were to draw in this tangent line and approximate it, I should get a positive value. Similarly, over here where I'm increasing, my derivative needs to be positive because my function is increasing. So I'm going to be positive on this interval. And then finally, when I'm at that point where I turn around, right, the point that's not included in any of my brackets here, that's where the derivative equals 0. So it's going to equal 0 here, here, and here. Okay, and so specifically that happens at x equals negative 1.5, x equals 0, and x equals 1.5. So wherever we turn around from increasing to decreasing, that's where the derivative equals 0. Okay, so again, derivative's negative here because I'm decreasing, positive here because I'm increasing, negative here because I'm decreasing, positive here because I'm increasing. And again, we're talking about the derivative as a function. So we're saying that if we were to be able to plot the function, right, then our function would be negative if we were drawing it, which is going to be our next step. Okay, so when we have any particular graph of f of x, we should be able to partition it off into increasing and decreasing intervals, which will help us understand the sign of the derivative. Okay, so for the next example, I'm going to come back to this in a second. We're actually going to start with a different first part, and then we'll come back to that picture in a minute. So our goal now that we have some sense about the relationship between a function and the derivative is going to be for us to take a function, much like this, and to graph the derivative of that function. Okay, so we're sort of going to be putting together all the pieces of the things we've learned up until now. So the first thing I want to sort of point out is where our function is increasing and decreasing, right? So again, I want to sort of partition this off. I can see that I'm decreasing here, and then I'm increasing here, right? And the other piece that's important here is the point where I turn around, where that derivative is 0, okay? So when I'm decreasing, I know that my derivative is negative. When I'm increasing, I know my derivative is positive. So what does that mean? How do I translate this into a picture, right? So what I want to mention here is that when we draw the derivative, we are translating what's happening at the independent value, and then the plot in terms of the dependent value is the slope of the tangent line at every point, okay? Which means that the easiest and best way to start this problem is to find the zeros, because that's the easiest one to calculate and to translate directly. So when x equals 0 is when the derivative equals 0. So I come over here to the origin, and at 0, I plot a 0. Okay, so that's the direct translation of this particular point. Now, to the left of 0, my function was decreasing, which means that my derivative has to be negative. So what does that mean? That means it needs to be somewhere down here. Okay, this is where values are negative. Negative values are below the x-axis. To the right of 0, my function was increasing. Therefore, my derivative needs to be positive, which means to the right of 0, I need to be somewhere over here, okay? Because these values are positive. They're above the x-axis. So how do I figure out how to draw a picture that's somewhere down here and ends up over here? Well, this goes back to approximating that derivative, right? Like we did before. So I want to pick a couple values to kind of get a sense of what's going on. So this is counting by ones across the bottom here. So let's go ahead and pick the value of 2. So if I go up here to my actual function, I'm going to pick the point -2, 2. And you can pick any point you want. It doesn't have to be the same point as me. And I'm going to draw on a tangent line. So let me grab my index card here. So like I mentioned, if you're doing this on paper or even on a computer, sometimes it's helpful to have an index card to sort of sketch this out. Okay, so I'm going to draw in a tangent line. So my tangent line is going to look something like this. Let's see. So I'm going to sketch this in. Make it as close as possible. Oops. okay? So I know I have the point negative 2, 2. That's the point where it touches. And then down here, it looks like I have the point negative 1, negative 2. Actually, I'm not sure you can see that, so I'm just going to write it down here. Negative 1, negative 2. So what that is going to do for me is it's going to tell me the y value when x equals 2. So I find the slope, right? The change in y over change in x. So 2 minus negative 2, right? So 2 minus negative 2 divided by negative 2 minus negative 1. I have to be really careful here with all my negatives, but I know that the value should be negative because it's downward sloping, and I know I have to be down here. So 2 minus negative 2 is positive 4. Negative 2 minus negative 1, those are going to cancel. That gives me negative 1, which gives me a negative 4 value. So I come over here and I go negative 1, negative 2, and I know the y value, which is the slope, has to be negative 4. Negative 1, 2, 3, 4. So that's a point I know, okay? Now, realistically, I'm not going to do this for every single point, right? I'm not going to be able to do this for every single x value. So typically, I just pick a couple. I'm going to do one on the other side, and that's going to give me the basic shape of the graph. So on the right-hand side of this graph, let's say I pick, 1 instead of 2 this time. So over here, this is the point, and I'm going to write up over here. This is the point 1, comma, that looks like negative 1, right? That's this point here. And I'm going to draw on a tangent line to that point to the best of my ability. Again, I'm going to use some sort of straight edge here. And you can probably tell that this gets sort of messy as you try to do this analysis. So here, this looks like a pretty good second point. This is 0, negative 3. So again, I'm trying to approximate the value at x equals 1 so I can figure out where to plot it. So my 2 points are 1, negative 1 and 0, negative 3. So my slope here, change in y over change in x. So I'll have negative 1 minus negative 3. So that's here. So I have to start with 1 on the bottom minus 0. Again, be careful with your negatives. Those are going to cancel. So I have 2 divided by 1, which gives me a slope of 2. So that means when I come over here and I go to x equals 1, that's where I approximated this, the slope is 2. So that's what I'm plotting here when I'm plotting the derivative. So you can kind of see that this is looking pretty linear. So I know my function has to go through these points. So a pretty good approximation of this when you have a U shape is to connect these points. Okay. So what was the process here? Again, I started with my 0. Where is the horizontal tangent line in terms of x? Then I plotted that. Then I approximated a point roughly to the left and roughly to the right to figure out roughly what my function would look like. And the conclusion is if my original function has this U shape, the derivative is linear through the 0, right? Through the place where I had the horizontal tangent line, okay? This is not easy at first. However, once you do a couple of these and you get the hang of it, it gets a lot easier. So if this seems really intimidating right now, there's a lot of things we learned today that we're putting together. I promise that if you sit down and did like 6 or 7 of these, that it would be much more straightforward. So if it feels overwhelming at first, that's normal. It does get better with a little bit of practice. So I want you to try this second one, sort of doing the same type of analysis that I just did before. So this is the original function. We're trying to plot the derivative. Okay. I want you to start by finding the zeros. Start with zeros. So where is that horizontal tangent line? Then I want you to approximate at 2 points and plot them. and then see what you get, right? You can also think about intervals where we are increasing and decreasing to try to figure out where our function will live. Okay, so I want you to take about 2-3 minutes, see if you can work this one out, right? It's going to be similar to this one, but this is a slightly different function, and see what you get. And then we'll go through it together. All right, take about 30 more seconds to finish up whatever part you're working on. All right, so again, the easiest way to start this is to figure out where the zeros are. And again, that's where we change from increasing to decreasing. So again, this happens at x equals 0. It happens at the origin. So when x equals 0, the derivative equals 0. So that's where we have to cross through. Because I start off increasing to the left, I know that I'm going to have something positive to the left of 0. So I decided to pick the point x equals -1 to approximate a point. Again, you could pick -2, really any point to the left of 0. And so I want to know for x equals -1 what the slope of the tangent line is, because then I'm going to go to -1 and I'm going to plot that value. So when I drew in my tangent line, I have the point -1, 0. That's where I touch. And when I drew in my tangent line, it looked like it also went through 0, 2. Again, yours might be slightly different than mine, but they should be positive and in the realm of what I'm getting. So here, if I calculate the slope, the change in y over change in x, I get 2. So when x equals -1, the derivative is 2, because that's the slope of the tangent line at -1. So I go to -1, and I go up to +2, and I plot that point. Similarly to the right, I decided to pick the point x equals 2 to approximate, right? So I'm interested in what's happening at x equals 2. So I draw in the tangent line. It looked to me like it went through the point 2, -3, and the point 1, 1. So here, I plugged in change in y over change in x to approximate, and I got -4. So when x equals 2, y should equal -4. Okay, and again, since I'm decreasing here, I know these values are negative, so that's in line with what's going on. So again, this looks pretty linear to me. So if I connect these points, the test points, I get a derivative that looks like this. Okay, so again, roughly linear. And now what I see is that my line is downward sloping if my U is upside down. If I have a hill, I have a downward sloping line. If I have a U, I have an upward sloping line, okay? And so what I want to do is I want to take that pattern and I want to be able to break down bigger graphs into these U's and hills so that I can sketch a derivative. So that brings us to this original picture that I said we were going to circle back to. Notice here that I have some U's right here and here, and then I have a hill in the middle. So when I have U's, I have something that's roughly linear in the upward direction. Same thing here. And when I have this hill, right, this downward sloping hill, then I have something roughly linear in the downward direction. And what I do is I sort of smooth out those lines, right? We don't want sharp edges because these are curvy, but it's the same translation. So if you have a U, you have an upward sloping line. If you have a hill, you have a downward sloping line. And then we just sort of connect the curves smoothly, right, to make the full picture. So this is the derivative here, okay? So we'll be practicing this quite a bunch throughout this course. You'll have a chance, but I definitely recommend practicing this on homework sooner rather than later. The sooner you apply this and try it, the better it'll go, okay? Have a great weekend, and we'll pick up with the next section on Tuesday.